Yesterday, we talked about preparation of salts. We had already talked about the addition of a metal to an acid. Yesterday, we covered making carbonates by adding a carbonate to an acid, and then neutralization by adding an acid and alkali. So an alkali is a soluble base. We talked about the theory of titration, though not in detail. And then, right, adding an insoluble base to an acid to make a soluble salt, and reactions of bases with ammonium salts. Today we'll be starting off by talking about how to make insoluble salts. So to adjust this for some reason every time. Preparing insoluble salts. So how do we go about doing that? For example, we want to make a salt called barium sulfate. Okay, barium sulfate. Right now, this is an insoluble salt, which means when you mix your reactants, this thing will form a precipitate. So it will be a solid and it will precipitate out of solution. Right? The solid will come, form and settle or be suspended in the aqueous solution. So what you do is that you take two salts that would give you barium sulfate. So you can start off with barium chloride, for example. And you can mix it with sodium sulfate. Right now, if you just go back to the solubility of salts, all sodium salts are soluble, so that's fine. All chlorides are soluble except for lead and silver. Now here we have barium, so that is soluble. So these two are soluble, right? Solutions, sodium sulfate and barium chloride. When you mix these two, what you're going to end up with is barium sulfate, which is what we want. And sodium chloride. The equation looks like this. You've got BaCl2, which is aqueous, plus Na2SO4, which is also aqueous, giving you BaSO4, which is a solid, it's insoluble, and NaCl, which is aqueous. Now this thing is not balanced. Aram, would you like to balance this?
Yeah,
Go ahead.
like there are two chlorine on the reactant side.
Okay.
No,
Yes. There's two chlorines over here and one chlorine over here. So what do you want
oh,
to do?
and yeah, like there are also two sodiums on the reactant side.
Two
So we are
sodium. So all right, we had
two.
two over here.
Yeah,
All right, so that's all we need to balance it. All right, so that's done. That's balanced. So this is the salt of interest. Now the ionic equation for this, as we talked about yesterday, you asked, and yes, the ionic equation depends on what reactions happening, so it's different every time. So you've got, right, for the salt of interest, you have the barium ion reacting with the sulfate ion to give you barium sulfate. Right, that is the ionic equation. Now, right, even though we're calling this insoluble salts, in some cases, right, some insoluble salts do dissolve, right, in to a very, very small extent. And so in that case, they are called sparingly soluble. Right? For the major purpose of our syllabus, it's insoluble, but the fact that it does dissolve to a very, very small extent, right? I mean, it's so small, in 1 liter of water, so 1 decimeter cube of water, 1 decimeter cube basically means 1 liter, right? How much barium would dissolve? Only 2.2 into 10 to the power minus 3 grams. So if you open that up, that's 0.0022 grams. That's pretty small, right? So it's like a super, super tiny amount, but it does happen. Now, right, as a summary of what just happened over here, we can take a look, a generalized look at this kind of method of preparation by writing it this way. So you've got soluble salt plus soluble salt. You've got, let's say, soluble salt 1 plus soluble salt 2 will give you insoluble salt, right? And plus soluble salt 3. That's a new thing. And so you can write it as AX plus BY, kind of looks like algebra, will give you BX plus A1. Right, you can kind of write it this way. This is the same way it's given in the book, right? Just for understanding what's going on. So, right, you're basically having the ions move about. Any questions?
No.
Okay, next up, testing for ions. Right, so you're given a compound, or you have a compound. Which ions does it contain? So the first of, we will, and, this is basically used to identify the anion part of the salt. What's the anion? The anion is the negative ion, negatively charged ion. Right, so for example, the sulfate or the carbonate or the nitrate, So let's start with testing for sulfates. Right now, we've seen that barium sulfate is insoluble. We've just seen that. And so basically what we're going to do is we're going to add a soluble salt of barium, just like barium chloride. We're going to mix it with the unknown and see what happens. Right? So you basically add soluble barium salt, right, such as barium chloride, to unknown salt. Right? That's also going to be a soluble salt. If a white precipitate forms, that will be barium sulfate. Right, which means the SO4 minus sulfate ions were present. So it was a sulfate salt.
The ions of the element are fixed or like do they change?
Just a sec. They were present in the unknown. Okay, the ions of elements are, for example, Na plus and Cl minus, right? So
Yeah.
it depends on what kind of ions, right? So for example, Cl minus is called the chloride, and so that's it. Then you've got the CO3 2 minus. This is called a carbonate. The carbonate ion always looks like this. So it's not that sometimes it becomes CO4 minus or something. It doesn't change. If it's different, so for example, you've got SO4 2 minus and SO3 2 minus. These both are different. It's not that one is changing to the other just like that. If it is changing, then some sort of reaction must have occurred to cause that change. It's not going to happen on its own. Oh, I don't feel like being SO4. I want to be SO3. It doesn't work that way. Okay?
Yeah.
Just get this out of the way. So basically, right, if you take a look at the ionic equation, what you're doing is you're taking the barium ion and you're taking the sulfate ion and you're forming insoluble barium sulfate. Right, so that's Ba2 plus SO4 2 minus, giving you BaSO4. Simple.
Yeah.
Okay, now it doesn't end here. When you have this white precipitate, you add a few drops of hydrochloric acid, right? Dilute hydrochloric acid. And so you want to notice what happens. So if after adding it, the precipitate does not dissolve,
What's a precipitate?
does not dissolve, that is barium sulfate. A precipitate, as I mentioned, right, is a solid that forms out of an aqueous solution. Okay, so you're mixing two liquids together and a solid is forming. That solid that's forming, and it might stay suspended in the liquid, or it might settle to the bottom of the the apparatus. It depends, but it's that's what's called a precipitate. Okay.
Yeah.
If it does dissolve, if on the addition of dilute hydrochloric acid, if the precipitate dissolves, then it's not sulfate. Right? It could be, for example, sulfite. So that is SO3, which I just mentioned, SO3 2 minus. So that's a different ion. Okay. Okay. Next up is testing for chloride. So that's Cl minus, bromide, which is Br minus, and iodide, which is I minus. So what you do is you take a suspected chloride, solution, suspected, so you're guessing, and you add dilute nitric acid, a small volume. Dilute nitric acid. Okay, and what will happen is the solution will become acidic, obviously because you're adding an acid to it. Then you add some silver, a soluble silver salt, right? So a small amount of soluble silver salt. If this is a chloride, we know that silver chloride is insoluble. We know that. How do we know that? Because we talked about it earlier. Just going back, right? All chlorides are soluble except for lead and silver. So silver's chloride is insoluble. So you took chloride solution, so it was a soluble solution. You acidified it by adding nitric acid. Then you added a soluble silver salt. Right? And so what's going to happen if a chloride was present over here, it's going to react with the silver, and it's going to give you a white precipitate of silver chloride. Okay, and so the ionic equation, you've got chloride in your unknown, aqueous, right? And you've got silver, also aqueous, and that's going to give you silver chloride, which is a precipitate. Right? So chloride ion, silver ion, giving you silver chloride. Similarly, right, so silver chloride is white, and if left to stand, so you just leave it, right, it turns gray. So that was for chlorides. Now, similarly, you can do the same thing for bromides and iodides. And right, you use a soluble silver salt for both of these, and you will get insoluble silver salts precipitating. How will you tell the difference between these two? Right, the silver bromide has a cream color, so AgBr silver bromide has a cream color, so it's not white. And silver iodide is yellowish, so it's a yellow precipitate. Alternatively to all of this, instead of using silver, use lead nitrate. All nitrates are soluble. You use lead nitrate, right, for iodine. So for the iodide. And it will give you a yellow lead iodide precipitate. Right, so PbI2, that's lead iodide. Any questions?
No.
All right. Third, testing for carbonates. Right, that's CO3 2 minus. And so basically what you want to do is you take, right, a suspected carbonate and you add a little bit of acid to it. And the carbonate can either be a solution or it can be a solid. Both work. And what you're going to notice is effervescence. Effervescence of carbon dioxide gas. Right, and if it is carbon dioxide gas, you can pass it through lime water, right, and it will turn cloudy or milky. Right, why? Because it's forming insoluble calcium carbonate. That's CaCO3, calcium carbonate. What does the equation look like? You've got carbonate ions, you've got hydrogen ions, acid, and they're giving you carbon dioxide and water. So you've got the CO3 2 minus plus the 2H plus, giving you CO2. So this might be aqueous or solid, depends. Let's say it's aqueous. This is definitely aqueous. This is a gas, and water is a liquid. Any questions?
CO3 was aqueous, but CO2 was gas. Is a gas.
CO2 is a gas, yes.
Okay.
Right? And so basically what's happening over here is reduction. Fourth, testing for nitrates. So as you can see, as you mentioned, these are all anions. These are all negative ions. The nitrate, NO3 minus, right? The CO3 2 minus, the chloride, bromide, and iodide, the sulfate, right? That's the SO4 2 minus. So these are all anions, all negatively charged ions. Okay, how are we testing for nitrates? You add aqueous sodium hydroxide to a nitrate solution. To the suspected nitrate solution, and you add aluminum foil or aluminium foil, and you heat it gently, right? So warm gently. What you will notice is, right, ammonia gas will be produced. We've talked about ammonia yesterday. It has a pungent smell, so that's one thing. And right, you can also test it with damp litmus paper. So damp litmus or indicator paper. And it will go from red to blue. And so what's happening over here is that the nitrate ions are reduced. And this is what the equation looks like, right? So it's a long equation, and I'll write it out balanced. You've got 3 NO3, right? We're writing the ions over here, plus 8 of aluminum, that's a solid, plus 5 of the hydroxide we added, and 18 water. All right, so these are the reactants. And so what you're getting out of this is 3 ammonia molecules, which is a gas, and 8 hydrated aluminum. or in fact, I shouldn't call it that, right? So basically what you're getting is this. Aluminum, right? OH4 minus, right? And so this, right, the production of the ammonia gas is what's going to tell us that, oh, it was a nitrate. Now, as I mentioned, nitrate ions are reduced. How are they reduced? Right? They have taken up hydrogen. Right? So the oxygen is removed and hydrogen has been added. So that is reduction. Now, if we go back to talking about whatchamacallit, oxidation and reduction, right? And so finally we have all the different types: oxidation and reduction. So recalling from what we already know, oxidation is the loss of electrons, reduction is the gain of electrons. Right? It is an increase in oxidation number, it is a decrease in oxidation number. It is a gain of oxygen, obviously. It is a loss of oxygen. It is a loss of hydrogen. It is a gain of hydrogen. As you can see, right, so it's the opposite thing. What you just saw with nitrate turning to ammonia, it gained hydrogen, it lost the oxygen. So the opposite, right, is oxidation, gaining oxygen, losing the hydrogen. Right, so these guys are opposites. And so any of these happening would constitute either oxidation or reduction. Any questions?
No.
Okay. Now the final topic that we'll be covering for this chapter, there is something I'm leaving for later, which is the detail of the technique of titration. So I'll come back to that later after we've gone through this chapter 4, stoichiometry. So we'll come back to that. For right now, the last topic of the chapter and the class is water of crystallization. So what happens? Sometimes crystals of salts, when you dry them out, right, when the precipitate forms and you filter them and you dry them with the tissue and everything, sometimes they form without water. And in that case, they are called anhydrous. An meaning no, and hydrous meaning water. So they don't have any water in them, right? They're called anhydrous. But right, many of the salts are actually hydrates. Right, many salt crystals are hydrates, which means, right, they have water in them, right? And that water is incorporated. So it is part of the crystal structure. This water that's part of the crystals of salts is called the water of crystallization. Oops. Crystallization. And because it is part of the structure of the crystal, the shape of the crystal, right, and the color as well depends on the presence of water. So an example is, right, crystals of copper 2 sulfate. So copper 2 sulfate crystals, look, you got the copper 2 sulfate, which is like this, and to show the water of crystallization, you put a dot, and then you write how many water molecules are associated with each crystal. So this is specific to the type of crystal, the type of salt, the compound, the molecule, right? This is you can't just put any number you want. So there are 5 water molecules that go with copper 2 sulfate, right? And if you have like cobalt 2 chloride, cobalt, right, chloride, it looks like this. So it is COCl2 dot 6H2O. So this guy takes 6 water molecules in its crystals. So it's specific, right? And in that case, this is called, right, copper 2 sulfate pentahydrate. Penta meaning 5, hydrate meaning water. So it has got 5 water molecules over there. Okay. Any questions so far?
Yeah.
Now you can remove this by heating. So when a hydrate is heated, the water of crystallization evaporates, right? And so you will end up with, uh, right, an anhydrous salt crystal. For example, copper 2 sulfate is blue. right? The hydrate. So you heat it, and in this case you need to heat it strongly, right? That's not doesn't mean you're trying to melt it or boil it, right? You're giving it strong heat, and it loses its water, and
The crystal salts are a chemical reaction or a
what I'm talking about right now, it's not a chemical reaction,
oh, sorry.
right? So this guy is blue in color. Copper 2 sulfate is blue. Copper 2 salts are blue in color. When you heat it strongly, right? As I mentioned, the water molecules, the water crystallization has an effect on the shape and the color. So you're removing the water of crystallization, and so it will make anhydrous copper 2 sulfate, and the color also changes. It's white now. Right, so it looks like this. CuSO4 5H2O. You're heating it, and you're getting CuSO4, which is a solid, plus 5H2O. So as you can see, it's not a chemical reaction, just separating the two. And because the water is evaporating, this is water vapor, so it's going to be a gas. The opposite happens when you add water to, so you can reverse this. You add water to anhydrous copper 2 sulfate. It will regain the water of crystallization, and turn back blue. But just to keep in mind that this process is extremely exothermic. So it's going to give up a lot of heat. It's going to become hot. So something to be careful about. Extremely exothermic. So thermic means heat. Exo means out. So it's giving out heat. All right. Now, because the color change of anhydrous copper 2 sulfate from white to blue is only happens when water is present, because getting the water crystallization back. So this particular change in color can be used to test for the presence of water. Right? So this color change from white to blue for the anhydrous to become hydrous again, right, can be used to test for presence of water. And so this is what it looks like, right? You've got copper 2 sulfate plus water, and that's going to give you hydrated copper 2 sulfate, or copper 2 sulfate pentahydrate. And notice this over here, right? This is the symbol for a reversible reaction. Right, so the reactions that we've talked about earlier, for example, they are not reversible. Once it happens, you can't simply go back the same way. You can go back, but not the same way. In this case, right? It's reversible. It's easy. It happens both ways. There's no major chemical, like there's no chemical change happening. Chemical reactions can also be reversible, but the point is to introduce the concept of reversible reaction. So this thing can go both ways. You heat it, you lose the water, you add the water, you get the hydrated crystal back. Any question?
No.
And we're done, right? So that, as I mentioned, I'm leaving the topic of titration for later. So we are done with this chapter and for today's class as well, right? So have a good weekend and I'll see you next time, inshallah.
Yeah. Allah Hafiz.
Allah Hafiz.